Hello students, welcome back. We just completed section 1, exponential functions. Now let's go to section 2, logarithmic functions. Here's the definition. A logarithmic function of base a is defined as the inverse function of the corresponding base a to the x power. Same base a. Because the definition is from the inverse function, all the properties of the inverse functions apply here. The domain of logarithm is the range of the exponential, and the range of the logarithm is the domain of the exponential. Just flip-flopping because they are inverse of each other. We'll come back to that in a moment with graphs. Now let's go to the second line here, the cancellation rule. Inverse of each other, so f inverse and f cancel each other out. Either way, one after another. So log a of a to the x power, after cancellation, we just have x. A to the log a of x, again, after cancellation, we just get x. One of more important application is down here. A to the 0 power is equal to 1, and I don't see a lot of mistakes there. Yes, I sometimes see people writing a to the 0 power is equal to 0, but that's rare. As for log of 1, well, log of a of 1 is not 1, it's 0. How do I do that? 1 is equal to a to the 0 power. And then after that, you can use this cancellation rule. Log and exponential cancel each other out. We just get 0. Let's come back to this. Domain becomes range, range becomes domain. Okay, that's what the original and inverse functions do. But which is which? Let's answer the question graphically. Okay, here's a standard case, which applies for 95% of the time, or even more. A to the x power. When a is greater than 1, we have strictly increasing function from 0 to infinity, or actually near 0 to infinity. Never mind, 0 to infinity. 0 is when x is negative infinity to positive infinity, alright? Now, here is a logarithmic function, and the location is because of the symmetry. Symmetric with respect to the principal diagonal because we have inverse function. Remember, original functions and inverse function, they are related with respect to the reflection on the principal diagonal y equals to x power. The reason is because what does inverse functions do? X goes to y and y come back to x. That's basically clear, isn't it? Let's look at this graph paper. X-axis is folded right onto y-axis if I fold over like this, and vice versa. So this reflection or this folding up is precisely what the inverse relation is all about. So the graph of this blue exponential function is going to be folded right on top of the graph of the logarithmic function red, and vice versa. Alright, we have all this symmetry, the graph, everything, alright, and then let's consider the domain and range. Look at the picture. Do you see the domain of the logarithmic function is 0 to infinity? Do you see that? Just by looking at the graph. You should. You have curve only on the right hand side when x is greater than 0. Nothing here. When x is equal to 0, undefined, going down to negative infinity. So we have to have parenthesis, not bracket. On the other hand, look at the range of the exponential function. Do you see that is 0 to infinity? The same range, so allowed y-coordinate value, all positive here, and never negative, and never hitting 0. This is just horizontal asymptote. So yes, 0 to infinity. You can see that from the graph. So that for the domain, and that for the range, and this is for logarithm, this is for exponential. Now how about the others? The range of logarithm all the way down to negative infinity, and this one goes to positive infinity. So we have negative infinity to positive infinity. How about the domain of the exponential function? Look at this blue graph. Negative infinity to the left, positive infinity to the right. You can go on forever either way. So yes, you can see those from the graphs. So by looking at this graph, you can easily retrieve these information. So it's going to be a lot more effective trying to understand from this graph rather than just memorizing this without graph. It's not that effective. Now this kind of thing, formulation is going to be more effective, you see. Just cancellation. But for domain and range, those kind of things, study with the graph. And this is very, very important graph. Standard case when a is greater than 1. Now the second graph here is not even half important, or actually much less. I'll say 95% of the time this, and the other is 5% or maybe even less. When a is less than 1, we have decreasing, so we have things like these. But it turns out considering things like this is going to be totally unnecessary because we can always change base into something more standard. We'll talk about it a little bit later about change of basis theorem. Anyway, here's very, very important graph, and then a special case of that very, very important case is repeated here when a is e 2.718, natural exponential case. Similar graph as before, similar properties. Importance of natural logarithm. Well, if you pick up your calculator, then you can find out ln symbol. Oh, wait a minute. I didn't really talk about ln symbol, excuse me. I should have, sorry about that. The special case when base is e 2.718, then instead of writing L log g base e of x, we simplify it as ln of x. So this expression here, ln, is just a shorthand of this. And all the days when people had to typeset this kind of subscript with some really strange typewriters and stuff, this was really effective writing. But nowadays, well, it became kind of tradition. Okay, we went through the definition and the graphs and then the natural logarithms. One more step to go, that is logarithmic rules. Properties of log functions. Ready? Okay, here's a warming up. Exponent rules. I hope everybody remembers. If you don't, stop the playback and review a little bit before starting. Okay, here are some log rules. First, cancellation rules, and we already discussed it. Log and exponential are inverse of each other, so they just cancel out. Either way. Now, here are two special cases. Log a of a is equal to 1. Why? A can be rewritten as a to the first power, and after cancellation we just get 1. You see, nothing is there, then 1 is hidden. Next. So 1 can be rewritten as a to the 0 power, and after cancellation, log a and a to whatever power cancellation, we just get 0. Okay, cancellation rule. And by the way, these are the corresponding rules for natural exponentials and the natural logarithms. Instead of L log g base of e, we have ln, but that's about it. No significant difference. Next, the standard rules. Oh boy, here are some really, really, really important formulae. There are 3 of them. Log of x times y is log of x plus log of y. So multiplication becomes addition. Log of x over y is log of x minus log of y. So the division becomes subtraction. And log of x to the k power is k times log of x, so any power becomes coefficient, and k doesn't have to be integer. For example, if this is the square root of x, for example, then this is 1/2 power. That's the same as 1/2 times logarithm. If this is, say, 1/3 power, then this is 1/3 times logarithm. So k can be any real number, actually. Doesn't have to be integer. Here are corresponding rules for natural logarithm. Instead of writing log of e, we can rewrite those into ln. And here's a fair warning. Log of x plus y is not equal to log of x plus log of y. And log of x times log of y is not equal to log of x times y. You see, if you have same algebraic operations, then that's wrong. We have to have change of operations here. Multiplication became addition, division became subtraction, power became coefficient. Finally, the change of base rules, and this one is not as important as the second rule, but it serves some practical purpose. For example, what if you want to calculate log base 3 of 17? Pick up your calculator, and if you're using TI calculator, I don't think you can do it directly. So you can change it into natural logarithm of 17 over natural logarithm of 3. Let me expand the font a little bit. Up is up, down is down. It's easy to remember. And then you can use your handheld calculator for natural logarithm. It'll turn out 2.83 something over, if I remember correctly, natural logarithm is in second floor function. There's something called log, which is actually the same as log base of 10, but I'm not going to use it in this course. Every time I have to do some computation, I'm going to convert everything to ln, and you should know how to use your own calculator. So calculate this, one over the other, and you're going to get 2.57 something. Yes, that's how you can do your computation, using the change of base formula here. So any logarithm, you can change it into natural logarithm. As a matter of fact, instead of 3, if you have something worse, like 1/3 like this, then you can do the same thing, because you see, base is less than 1. That's difficult to handle, as you saw in this kind of graph. But if you use the change of base formula, you can change everything to natural logarithm. So from here, no problem. It'll turn out it's going to be negative like this. Try on your own. As a matter of fact, do you wonder why did I get negative and how did I get this so quickly? So this was basically 3 to the negative first power. So this is negative 1 of log of 3. And that's how I figured, oh, I have to just put negative here, negative there, and that's it. So we went through all these log rules. Change of base, standard, that's the most important, and the cancellation rules too. Everything is important, and we are going to talk about how to utilize them in the next video.